Hey everyone, Mr. Dow here to talk about section 4.3, chain rule. We're going to need a new shortcut when dealing with derivatives, specifically when we have composite functions. Function within a function, something like the f of g of x, where g of x is its own function and f of x is its own function, and they're built within each other. For instance, if I have the f of x equals 2x plus 3 raised to the fourth. 2x plus 3 is its own function. Some quantity raised to the fourth is a secondary function. So I have a function within a function. I'm going to need a shortcut to help deal with that. Another example, if I had the ln of 3x plus 1. 3x plus 1 is its own function. The ln of x is also a function. Well, I have a function within a function here. Here's the setup for the formal definition for the chain rule. I have two functions, y equals f of u and u equals g of t, both of which have to be differentiable. And here's your formula. dy over dt equals the following. If the Leibniz notation is a little confusing for you, I could give it to you in function notation. Let's say h of x is the function that I'm going to take the derivative of. It's made of f of g of x. I'm going to have to take the derivative of the function on the inside, g of x, and then multiply that by the derivative of the overall function, the f of g of x. Let me show you a few examples to clarify. T plus 5 is a function. I can take the derivative of that function. Some variable raised to the third is also a function. That's my secondary function. I can think of it as y equals u cubed, and I can do a substitution where u is t plus 5. Take the derivative dy dt, I'm going to take the derivative of the entire function, and I'm going to multiply that by the derivative of the inside function. And I'm going to use the simple shortcut in doing both. The derivative of t plus 5 would be 1. The derivative of u cubed, or t plus 5 cubed, the 3 drops down in front of the entire expression, and I reduce the exponent by 1. I don't mess around with anything on the inside the parentheses. I've already done that. And then I can simplify all this. So here you have your answer. Dy dt is 3 times the quantity t plus 5 squared. Example 2. 4x squared minus x, all of that raised to the fourth. 4x squared minus x is a function. I'm going to take the derivative of that function. 2 comes down, multiplies by the 4 to get 8x. Reduce the exponent by 1. The 1 above the x comes down in front. Reduce the exponent by 1, x to the 0 is just simply 1. And then I'm going to take the derivative of the secondary function, which would be the parentheses treated as just a variable, u. So multiply by 4 comes down in front. Don't touch the inside, I've already taken care of that. And reduce the exponent by 1. You can rewrite your final answer if you want to. dy equals dy over dt equals. And let me review where I came up with each of those two parts. I took the derivative of 4x squared minus x to get 8x minus 1. And then I treat everything inside the parentheses like there's nothing even there. I take the derivative of essentially parentheses raised to the fourth. The 4 drop down in front. I reduce the exponent by 1 and just rewrite whatever's inside the parentheses. Example 3. I have two functions, y equals and x equals. I want to take the derivative dy over dt. To do that, I'm going to take dy dx and then multiply by dx dt. The derivative of the y function, 3 comes down in front, reduce the exponent by 1. The derivative of negative 3 is 0, that drops off. Multiplied by the derivative of the x function, 2 comes down in front, reduce the exponent by 1. The negative 1 drops off. If I wanted to express this in terms of t, meaning instead of having an x and a t in my final equation, I can substitute. By substituting, I have my final answer. Instead of having an x and a t in the final answer, I'm writing it in terms of t, meaning I only have t's. Well, I'm going to swap out the x for what I know x equals. And gives my final answer dy dt. Here's an example involving natural logs. In order to answer this problem, let's recall that if the f of x equals ln of x, the derivative f prime of x is 1 over x. My first function is x cubed plus 2. To take the derivative of x cubed plus 2, 3 drops down in front, I get 3x squared. And then I'm going to multiply by the ln of whatever's in the parentheses. And that derivative is 1 over x, which you can see as 1 over x cubed plus 2. You can multiply these two together to get your final dy over dx. Let's do an example involving e. Recall that if f of x equals e to the x, the derivative f prime of x equals e to the x. This is the function where it is its own derivative. X to the fourth is my first function that I'm going to take the derivative of. Negative 4x to the third is the derivative. And then I'm going to multiply by the derivative of the entire function. The derivative of e to the anything is e to the anything. So you get your final answer, dy dx, everything you see afterwards. Just to recap this one, derivative of negative x to the fourth, negative 4x to the third. Derivative of e to the anything, e to the anything. A function within a function utilizing the chain rule. Example 6. To take the derivative dy over dx of all three of these items, I'm going to take the derivative of each one individually. The derivative of 10 is 0. The derivative of 2x cubed is 3x squared. And the derivative of negative 5e to the negative 3x is going to have to use the chain rule. The derivative of e to the anything stays the same, but remember I have to multiply this by the derivative of the secondary function, negative 3x. And the derivative of negative 3x is negative 3. I'm going to have to multiply everything I see here in green. Negative 3 times negative 5 gives me negative 15 e to the negative 3x. Bring down the 3x squared. And I have my final answer. On second thought, looks like I made a mistake here. When I look back at my answer, I noticed when I was doing the shortcut, 3 times 2, silly me, I wrote 3. Clearly that's not the answer. 3 times 2 is 6. So my final answer, my fault, 6x squared minus 15e to the negative 3x. And you can check this out. Here's another one. Negative times negative, positive. So if you're wondering how on earth I made such easy mistakes, well, when I'm recording this, Mr. Morgan just walked in the room, and you guys know how he is, and I don't even need to finish that story. Last problem, I'm actually going to show you two different ways. One using the chain rule, one without. Using the chain rule, dy dx, the exponent, 2, comes down in front. I don't play around with the x plus 3. Take the derivative of the inside function. The inside function is x plus 3. Has a derivative of 1. Don't really need to write times 1 if you don't want to. So dy dx is 2, parentheses x plus 3. Here's another way you could have done it. You could have expanded the binomial. When you expand x plus 3 cubed, you would get square the first, double the product, and square the last. You can now take the derivative of each of these terms individually. The derivative of x squared is 2x. The derivative of 6x is 6. And you can see, if I would have distributed back the first time, I would have the same answer. First with the chain rule, second without the chain rule. Feel free to use either if you're not comfortable with the chain rule. And that just about does it on the chain rule for this time.